every type of large-scale cosmic structure. Space is complicated. We make it simple. Zoom out far enough, and galaxies stop being the biggest thing in the picture. At the largest scales astronomers can actually map, the universe isn't a random scattering of galaxies at all. It's an enormous thread-like structure with galaxies clustered along filaments, walled off around vast empty voids, all connected into something that looks disturbingly like a giant web or a brain or a sponge, depending on which astronomer you ask. We're going in order from the structures closest to home to the largest confirmed structures in the observable universe. Then we'll sort them a second way by how confident astronomers actually are that each one is real. Because on this list, officially confirmed and still seriously disputed sit right next to each other. The local group. We begin close to home with the smallest structure on this list, and also the only one small enough that a single mind can actually hold its entire membership in working memory. The local group is the collection of roughly 80 confirmed galaxies gravitationally bound together, dominated by two major members, the Milky Way and Andromeda, along with dozens of much smaller dwarf galaxies orbiting one or the other. Here's the fact that should genuinely bother you. This entire collection, 80 galaxies and everything in them, spans only about 10 million light years across. A distance that sounds enormous until you realize it's essentially the smallest unit of large-scale cosmic structure that exists, the equivalent of a single grain of sand in every comparison that's about to follow. Here's the part that lingers. The local group isn't static. It's gravitationally bound tightly enough that it will eventually collapse further inward on itself over billions of years, with smaller galaxies continuing to merge into the two dominant members, and Andromeda and the Milky Way themselves eventually merging into one, meaning the local group's current membership list is really just a snapshot of an ongoing slow motion consolidation that started billions of years ago and won't finish for billions more. The Virgo Supercluster. Here's the twist. Our local group isn't a standalone structure at all. It's a minor suburb of something dramatically larger. The Virgo supercluster, sometimes now considered a smaller lobe of an even larger structure discovered more recently, contains roughly 100 galaxy groups and clusters, including the local group itself, spanning somewhere around 110 million light years across, anchored gravitationally by the massive Virgo cluster near its center. Here's the fact that should genuinely bother you. Despite its enormous size, the Virgo supercluster isn't actually a single gravitationally bound structure in the way the much smaller local group is. It's a looser, gravitationally influenced association, meaning it's currently being slowly pulled apart by the universe's overall expansion, even as its component parts remain locally gravitationally interconnected, a genuinely strange intermediate state between one object and just some galaxies that happen to be near each other. Here's the part that lingers. For decades, the Virgo supercluster was considered the largest structure our galaxy meaningfully belonged to, a status that turned out to be itself only a temporary understanding, waiting on a bigger telescope survey to correct it. Laniakea. Here's the reframe. In 2014, astronomers redrew the map entirely, and it turned out the Virgo supercluster was never the full picture at all, just one lobe of a dramatically larger structure nobody had previously mapped in full. Named Laniakea, Hawaiian for immense heaven, this newly identified supercluster spans roughly 500 million light years and contains approximately 100,000 galaxies, including our own Milky Way, the Virgo supercluster, and dozens of other superclusters previously thought to be separate independent structures. Here's the fact that should genuinely bother you about how this discovery was even made. Laniakea wasn't identified by simply mapping where galaxies are located in space. It was mapped by tracking the actual motion and flow of galaxies through space, the same way you'd map a river system by tracking which way the water is actually flowing, rather than just noting where the water happens to be sitting at a single moment. Every galaxy within Laniakea's boundary is gravitationally flowing in aggregate toward a shared regional gravitational center, and the boundary of the supercluster itself is defined by the specific dividing line where that shared flow gives way to galaxies flowing toward a completely different neighboring gravitational basin instead. Here's the part that lingers. This means Laniakea's boundaries aren't fixed by matter density in the way most maps of structure usually work. They're fixed by motion, by which direction billions of years of accumulated gravity is quietly pulling everything within it. The Great Attractor. Here's the pivot. Laniakea's shared gravitational flow has to be flowing towards something, and figuring out exactly what that something is turned out to be one of the more genuinely frustrating mysteries in modern astronomy. The Great Attractor is a region of unusually concentrated mass, sitting roughly 150 to 250 million light years away, whose gravity appears to be pulling the Milky Way, along with thousands of other galaxies across an enormous surrounding volume, steadily toward it. Here's the fact that should genuinely bother you. For decades, astronomers couldn't get a clear look at what was actually causing this gravitational pull, because the Great Attractor happens to sit almost directly behind the dense, dust-choked plane of our own galaxy from Earth's point of view. A region astronomers informally call the zone of avoidance, where the Milky Way's own stars and interstellar dust block most visible light from anything behind it. Only by switching to X-ray and infrared observations, wavelengths capable of penetrating that dust, were astronomers eventually able to confirm the Great Attractor corresponds to a massive, previously hidden concentration of galaxy clusters. Here's the part that lingers. Even after identifying it, some astronomers now believe the Great Attractor itself isn't the final destination of this gravitational flow at all. It may simply be a waypoint on the path toward an even larger, more distant concentration of mass discovered more recently, called the Shapley Supercluster, meaning the true endpoint of everything Laniakea is flowing toward might still not be fully settled. Cosmic voids. Here's the twist that flips the entire category on its head. Not every large-scale structure is defined by what's there. Some of the largest confirmed structures in the universe are defined almost entirely by what's missing. Cosmic voids are enormous regions of space containing dramatically fewer galaxies than their surroundings, sometimes stretching hundreds of millions of light years across, effectively vast, mostly empty bubbles carved out of the overall cosmic structure. Here's the fact that should genuinely bother you. The largest confirmed void, sometimes called the Eridanus supervoid or the cold spot region, spans up to nearly 2 billion light years and appears to correspond to an unusually cold patch in the cosmic microwave background. A genuinely disputed finding, with some researchers arguing it represents a real, physically enormous absence of matter, and others arguing it's more likely a statistical artifact or an unrelated foreground effect rather than a single coherent void at all. Here's the part that lingers. Living inside a void rather than within a dense filament or cluster would mean growing up under a night sky with dramatically fewer visible galaxies than we actually observe from Earth. Some theoretical work has gone as far as suggesting that a civilization evolving deep inside an unusually large, empty void might never develop cosmology as a science at all, simply because there wouldn't be enough visible structure around them to notice the universe was expanding in the first place. Galaxy filaments and the cosmic web. Here's the fact that reframes every structure discussed so far as part of one single unified pattern. Superclusters, voids, and everything in between aren't separate, unrelated categories. They're all part of one continuous universe-spanning structure called the cosmic web, in which galaxies and galaxy clusters are arranged along long thread-like filaments, stretched between the walls of enormous voids, meeting at dense nodes where multiple filaments intersect. Here's the fact that should genuinely bother you. This entire structure isn't random. It's the direct, computationally reproducible result of how gravity acted on the universe's very earliest density fluctuations, the same tiny variations visible in the cosmic microwave background. Regions of slightly higher density attracted more matter over billions of years, growing into filaments and clusters, while regions of slightly lower density lost matter to their denser neighbors and slowly hollowed out into voids. Modern supercomputer simulations of the universe's evolution, run purely from the physics of gravity and the initial density map, reproduce a cosmic web strikingly similar to what large galaxy surveys actually observe, strong evidence that this entire universe-spanning structure is simply gravity, acting patiently for over 13 billion years on a slightly lumpy starting point. The Hercules-Corona Borealis Great Wall. Here's the fact that closes this list on its most disputed, most extreme note. Discovered in 2013, the Hercules-Corona Borealis Great Wall is a proposed structure of galaxy clusters so enormous, estimated at roughly 10 billion light years across in some measurements, that it would represent nearly a tenth of the entire diameter of the observable universe packed into a single connected structure. Here's the fact that should genuinely bother you. A structure of that scale directly challenges a foundational assumption in modern cosmology called the cosmological principle. The idea that on the largest possible scales, matter in the universe should be distributed roughly uniformly, with no single structure large enough to represent a meaningful fraction of the universe's total observable size. If the Hercules-Corona Borealis Great Wall is confirmed at its largest proposed scale, it would sit uncomfortably close to violating that principle outright. Here's the part that lingers: its exact size, and even whether it should be considered one single coherent structure rather than several separate, coincidentally aligned ones, remains a genuinely active, unresolved dispute among astronomers, making it, of every entry on this list, the one most likely to either be confirmed as the largest known structure in the universe or quietly downgraded and reclassified, depending entirely on what the next generation of galaxy surveys ends up finding. Galaxy clusters and the intracluster medium. Here's the fact that fills in a piece of this puzzle most people overlook entirely. The space between galaxies within a dense cluster isn't actually empty at all. Galaxy clusters, the dense nodes where the cosmic web's filaments intersect, contain not just hundreds or thousands of individual galaxies, but also an enormous reservoir of superheated gas called the intracluster medium, filling the space between them at temperatures reaching tens of millions of degrees, hot enough to glow brightly in X-rays even though it's completely invisible in ordinary light. Here's the fact that should genuinely bother you. This superheated gas actually outweighs the combined mass of every visible star in every galaxy within the cluster, making the intracluster medium the single largest reservoir of ordinary, non-dark matter in the structure, even though it took X-ray telescopes rather than any optical instrument to reveal it was there at all. Here's the part that lingers. Galaxy clusters are also where astronomers first gathered some of the strongest evidence for dark matter's existence, because the total gravity needed to hold both the galaxies and this superheated gas together without everything simply drifting apart is dramatically more than the visible matter alone could ever provide. Let's sort these 8 again, a different way, not by size, but by how confident astronomers actually are that each one is real. On the fully confirmed end, the local group, the Virgo Supercluster, and Laniakea, all directly mapped through observed galaxy positions and motion, with broad scientific consensus behind their basic existence and boundaries. On the confirmed but still being refined end, the Great Attractor, real and gravitationally confirmed, but with its ultimate relationship to the more distant Shapley Supercluster still being actively worked out. On the structurally essential but individually disputed end, cosmic voids, a real and confirmed category overall, even though specific individual examples like the largest proposed supervoid remain genuinely contested. On the theoretically necessary end, the cosmic web itself, strongly supported both by direct observation and by independent computer simulation, essentially the unifying framework tying every other entry on this list together. And on the most contested end of all, the Hercules-Corona Borealis Great Wall, a structure so large that its very existence, at the scale originally proposed, remains a genuinely open question rather than settled fact. It's worth pausing before we close on exactly how these structures were actually mapped, because the effort involved is almost as staggering as the structures themselves. Large-scale cosmic maps depend on surveys that record the precise position and distance of hundreds of thousands, sometimes millions, of individual galaxies, one at a time, each distance calculated from that galaxy's redshift, the specific stretching of its light caused by the universe's expansion. Here's the fact that should genuinely bother you. Even our most ambitious completed galaxy surveys have only ever mapped a small fraction of the observable universe in this kind of detail, meaning every structure described in this video, including Laniakea itself, was assembled from what is still, relative to the true scale of everything out there, an incomplete ongoing data set. The true shape of the full cosmic web in its entirety has never been completely mapped by anyone and may not be for generations. Here's the last thing worth sitting with. Every structure on this list, from the 80 galaxies of our own modest local group up to a proposed wall of galaxy clusters 10 billion light years across, ultimately traces back to the exact same origin. Tiny, almost imperceptible density differences in the universe's first few 100,000 years, patiently amplified by gravity for over 13 billion years into a web spanning the entire observable universe. You are right now sitting on a planet in a galaxy, in a group, in a supercluster, on a single thread of that web. And the whole structure is still slowly, quietly flowing towards something we've only partly identified. Not bad for stick figures on a rock.